Okay, for this video we'll be looking at dimensional analysis. In dimensional analysis we'll look at the quantities that we use in physics, and dimensional analysis is one way in which we can check the validity of an equation, as it allows us to check that the units on both sides of the equation are the same, and so you can see if an equation is valid using that technique. When we have units, we have our common SI units, right? And these are our Newton, the meter, second, yeah, etc. Right? And these units are internationally recognized. So wherever you go in the world, these units are valid in all scientific papers and stuff. We have other units as well that are not internationally recognized, like these are more common in like imperial countries like America. So we have the pound for weight, and they have the foot and the yard, all these, right? These are not internationally recognized, and other than America, I don't think they're used any other place in the world. I think there's one other country that also uses them, but pretty much no one else uses them. So the SI units is what we're mainly focusing on, and under these SI units, we have what's called as base units, right? And these base units are the meter, right? And that has a symbol of M. We have the second, that's obviously S, so that's symbol. The kilogram, which is kg, right? We also have the ampere, which is for electricity, amps, right? We have candela, which is a unit of brightness. So like how bright like a candlelight is, or a light bulb, right? We have the mole, which is used in chemistry, and it's a unit for quantity. And finally we have Kelvin in K. It's just Kelvin, not degrees Kelvin, just Kelvin, like 30 Kelvin, that's unit for temperature, right? All of our dimensional analyses will be used or made up of these base units. So we won't be using the SI units like Newton, we'll be using all of these, right? So if you start off simple, the dimensional analysis for force. So we know that force is equal to ma, and the base units for mass is kg, right? And the base units that make up acceleration is meters per second, right? We know that, that's simple, that's our units for acceleration anyways, right? And so combining this, we get kg meters per second, right? So this is equal to a Newton. Dimensionally, this is what a Newton equals. And we can get other equations for a force. We can get forces also equal to the change in momentum over time, right? And momentum, we know there's mv, so that means dimensionally that's kg meters per second, right? So that's kg ms minus 1. And then over time, that's seconds, right? And so we bring the seconds up, we can go that that's equal to kg ms minus 2. So you see how even though these are two different equations, we can check that the validity of that force is equal to kg meters per second. Moving on to energy, we can say that, get our first equation, we can say that work is equal to force applied over a distance. We know that force from literally before is kg meters per second, right? So we can get kg meters per second, right? And d is distance, which is just meters. And so we get kg meters squared per second squared, and that is equal to 1 joule of energy. So that is what a joule is equivalent to. And we can check this further using some other energy equations, such as potential energy, gravitational potential energy, right? mgh, our mass, which is kg, multiplied by g, which is our acceleration due to gravity, so that's just ms negative 2. And then we have our height, which is meters, right? And then again, we get combining all this together, you can see that we get kg meters squared, because that meters is times by that meters. So we get meters squared and then per second squared. We can go to another popular energy equation, which is kinetic energy. It's half mv squared. Now when we're doing dimensional analysis, we ignore all multipliers or all constants. So we ignore the half for this, right? And we get mass again, which is kg. V will equal to meters per second, right? We know that. So v squared will equal to this meters per second squared, which is just equal to meters squared per second squared, right? And so if we chuck that up here, we again get kg meters squared per second squared. Moving on to a slightly harder one now, we can get the kinetic energy in a spring, which is kx squared, or half, sorry. That's half kx squared. We know that k is equal to force applied over a distance, so F over x. So we can rewrite this equation, subbing this in to here. We can simplify this to half fx x squared. This cancels out with this, and we get half fx. Doing the dimensional analysis for this, we again ignore the half because it's we ignore constant multipliers. So we get force, which we know is kg meters per second, right? So we get kg meters per second times by, right, do the square brackets like we've always been doing, multiplied by x, which is distance, and again we get kg meters squared per second squared. So even when the formula doesn't quite look like the other energy formulas, we still end up with the same result dimensionally. So moving on to power now, we can say that power is equal to the change in energy over time. We know that energy, which we just did, was kg meters squared per second squared. So that would be kg meters squared per second squared. And that is all over t, which dimensionally is just seconds. So that is equal to kg meters squared per second cubed. All right, so now that we know what power is, we can check other power equations to see if they're still dimensionally the same as that equation. Another popular power equation is power is equal to the force times by the velocity, right? So we know that force is kg meters per second, right? Times velocity, which is meters per second. So we can get kg meters squared per second cubed. These are the same. Let's see. So as we know, power is in watts, so this is dimensionally equal to 1 watt of power. So, and same as this, we have one more for power, which is P is equal to IV. Now, this is using electricity now, so all the other ones, this was a mechanics problem. Now we're using electricity, so we can now still see that even dimensionally, because we're still using power, it's dimensionally the same thing. So for this, we have current, which we know is a base unit. Based on here, it's ampere, right? So we know that's a base unit, but we don't have a base unit for volts. So a volt is equal to the amount of energy per unit of charge. And so we know work, which is just energy, is what we have derived here, kg meters squared per second squared. But what's Q? What's a charge, right? A Q is equal to amp seconds, right? So IT, ampere seconds. So that means that a volt is equal to the amount of work over IT, and so power is equal to I WIT, right? And so we can cancel out these i's, right? And so power is just the amount of work done over time, and we get energy being kg meters squared per second squared over seconds. Bring this up to the top, and we get kg meters squared per second cubed. And so again, we still get the equivalent of a watt. Even though we're using electricity now, even though before we were only doing mechanics, even an electricity equation, or an equation that's meant to be used for electrical problems, is still dimensionally the same if it's using the same quantity, which is power in this case. Okay, so next we'll be looking at an equation that you've probably seen before. It's a kinematic equation. And through dimensional analysis, we can find that the units on both sides of the equation are actually the same. So we know that we're calculating a distance, which is dimensionally just meters, right? But on this side, it doesn't look like that we are calculating or adding distances together, but we should be in order for this equation to be dimensionally correct. And so we can break that down. So on this side of the equation, we got meters, obviously, because that's just distance. But that is equal to velocity, which is meters per second, times seconds, right? Plus, again, we ignore the half because it's a multiple constant, plus acceleration, which is meters per second, and then plus time squared. And so you can see that this seconds cancels out with this seconds, right? And so we're just left with a meter. And then this seconds, because it's squared, is cancels out with this. And again, we're just left with a meter. And so, in fact, we are just adding distances together to get another distance. So what this equation is actually doing is we have our x and our y values, and we have a projectile, right? We know this this equation calculates the distance traveled by a projectile and projectile motion. So we have a projectile. Let's say it ends right here, right? And we are calculating this distance. That is the distance that we're calculating. That is this d right here. And so what is vi doing? Vi is actually this distance right here. It goes sort of at a tangent. So that's vi. It should probably connect like somewhere over here, but whatever. I drew it trash. And then it comes back down. So oh sorry, that's vit, sorry, not just vi. And then it comes back down, and that is half at squared. Right? So what you get is actually like a vector where this is our d, this is our vit, and that's our half at squared. And so this, again, we know that vectors, you can only add vectors that are the same quantity. So these are dimensionally still distances. That's why we can add them as a vector. So if you made it this far in the video, I assume you're probably interested. So what I want you to do is try to find the base units. So construct a dimensional analysis for the unit C using from this equation right here. I'll probably write it out because it's kind of blurry. So Vt is equal to pi p r to 4 8cl. So we're trying to find this. So go ahead and do that and pause the video right now. Okay, now that we're back, I would rearrange for C to make it easier. So we got C is equal to pi p r4 times t over 8VL. We'll probably do capital L. As you know, or you should know by now, that pressure, which is the P, I'm pretty sure, yep, P is the pressure, is the amount of force applied over a area, right? So dimensionally that is kg meters, got it, kg meters per second over meters squared. which that just equals to kg meters to the -1, and then seconds to the -2. So that is our pressure. R, which is R to the 4, that is radius. So radius is in dimensionally is meters, so that's meters to the 4, right? T is just seconds, and L is just length, right? So that is again meters. So knowing this, we can reconstruct this equation using strictly base units. I would omit the 8 and pi, as those are again constant multiples. So we get C is equal to P, which is kg m to the 1, s to the -2, m to the 4, and then s all over v. Oh, we forgot volume. Volume is again meters cubed, right? That means meters cubed times length, which is just meters. And we can simplify that, so we get kg. Meters to the 1 times meters to the 4, we get meters to the 3. And then seconds to the -2 times seconds, we get seconds to the -1. That's all over meters to the 4. Kg, meters to the 1, seconds to the 1. And that is our base units for C. Sweet as.